finally, for the third of our common kinetic reaction orders, we'll talk about zero order. In this case, the rate is simply k, and if we go ahead and integrate this, we see that we're going to get the concentration of A at time t will be negative kt plus our initial concentration. And graphically speaking, that means that if we plot the concentration of A over time, you should get a line. Let's try that again. You should get a line, something linear. So this is the easiest one. It's a constant decline in concentration. So if we're going to go ahead and try the same numbers from before, it should work, but we'll find out. So at 510 degrees Celsius, like before, A is going to be 135 torr to start. K is 6.8 times 10 to the negative 4. Sorry, this will just be inverse seconds this time. No, it won't be, yeah, just inverse seconds. And then we have our, no, those are the three numbers we need. So A at time 1420 seconds. What's the pressure of A? We can go ahead and do this. Again, concentration and pressure are interchangeable for gases. This is the same reaction as before, which is a gas-phase reaction. So our concentration at time t, or we can say pressure again, will be equal to negative 6.8 times 10 to the negative 4 times 1420 plus 135. Let's go ahead and do it. Negative 6.8 times 10 to the negative 4 times 1420 plus 135. We get indeed 134 torr. So not much has happened in a zero order reaction here for this particular reaction. The rate law is, rate constant is too slow. It's a very slow process. So we see, generally speaking, zero order reactions are the slowest. First order are in the middle, second order reactions are the fastest, generally speaking. And so we're going to see here that we can solve this just like before. We just use our formula. In this case, the graph will be concentration versus time. That's linear. The other two graphs will be weird things. They'll have natural logs. If you do natural log and inverse, you'll get weird graphs. So again, you're looking for the one that's linear. If you find the linear one, that means that that's your reaction order. And that's it for zero order reactions. You can pause the video now, but just a fun fact. So interestingly, many biological reactions are zero order. The reason for this is because as things in biology encounter enzymes, enzymes are what allow reactions to happen within our bodies, within our cells. Many of them get saturated very easily. So even at low concentrations of reactant, your enzymes are overwhelmed. So they're just working as fast as they can. And so we see things overwhelmingly as zero order reactions. And one of them is the breakdown of ethanol. So if you consume alcohol, your body immediately starts breaking it down. But this is a zero order process. So your body actually is decomposing ethanol at the same rate no matter how much you have. Which is why we might expect if you get really drunk that you'll sober up faster. But that's not the case because it's zero order. It doesn't depend on concentration. So if you have 6 shots of something, please don't. It's not a good idea. It generally takes roughly about 6 hours for your body to work through that. If you take 1 shot, it'll take your body about 1 hour to work through that. And so it's simply just zero order kinetics. And this is something encountered by many enzymes in the body. So where the concentration of your reactant is not applicable to the rate. So zero order reactions definitely happen a lot, especially in biology, where we may not see them as much in chemistry specifically, It's simply because of the machinery involved, that when in biology you have enzymes participating, once those enzymes are filled up, then the reaction will not proceed. So it's really your enzyme that controls the rate of the reaction. And so once those are saturated, that's it. So just an example of zero order kinetics.